Hello students, so here we are with lecture 2 of electrochemistry. Now these are some of the questions from NCERT exercise based on what we studied in the lecture 1. So arrange the following metals in the order in which they displace each other from their salts: aluminium, copper, iron, magnesium and zinc. So what is going to decide whether they get displaced? Displace means they can displace the less reactive metal by a high reactive metal. That means they undergo oxidation. So more the reactivity, more is the tendency to oxidize. So their oxidation potentials are higher. So based on that, the arrangement will be magnesium, then aluminium, zinc, iron and copper. So we will have to check their oxidation potential. The one which has got the higher oxidation potential will undergo more oxidation. The reactivity towards oxidation will be more. So magnesium, then aluminium, zinc, iron and copper. Now given that electrode potentials are given for the cells and you have to arrange them in the increasing order of reducing power. So increasing order of the reducing power, that means we have to check their oxidation potentials. So oxidation potential is the reverse of the reduction potentials. Here the reductions of potentials are given and we will change the sign and then we will arrange them in the increasing order of the reducing power. So who will have the maximum reducing power? Potassium has got the lowest reduction potential, that means it will have the highest oxidation potential. Then it will be magnesium, then after that it will be chromium, then mercury and then finally silver. So this is the reducing order, increasing order of the reducing power. So depict the galvanic cell in which the reaction zinc plus 2Ag gives you zinc ions plus 2Ag takes place. Further show which of the electrode is negatively charged, the carriers of the current in the cell, individual reaction at each electrode. So the setup is similar as shown below. Zinc rod is dipped in zinc sulfate solution. Silver rod is dipped in silver nitrate solution. Both are connected by salt bridge and the two electrodes are connected by a voltmeter. Okay. So zinc is dipped in zinc sulfate solution. The cell will be represented as zinc solid, vertical line, zinc ions aqueous, double line, silver ions aqueous, silver solid. So the anode is what? Zinc electrode, which will be negatively charged. The current will flow from silver to zinc in the external circuit, that because the electrons are flowing from zinc to silver. Then at anode you have the reaction zinc gives you zinc ions plus 2 electrons. At cathode 2 silver ions plus 2 electrons gives you silver. So this will be our cathodic and anodic cell reactions. Okay. Okay, let's see the next question. Calculate the standard cell potentials of the galvanic cell in which the following reaction takes place. So 2Cr solid plus 3CD2 plus aqueous gives you 2Cr3 plus aqueous plus 3CD solid. So this cell reaction is given and you have to calculate the delta G and equilibrium constant. So for delta G, the formula is delta G is naught is equal to minus NF E naught. So you require to first calculate E naught cell. So E naught cell is equal to E naught cathode minus E naught anode. So for this particular reaction, Cr is getting oxidized and cadmium is getting reduced. Therefore, Cr is anode and Cd is cathode. So my formula will be what? E cell equals to E naught cathode minus E naught anode. So the potential for cathode is what? Minus 0.40 and for anode is minus 0.74. So minus 0.4 minus 0.74 is equal to plus 0.34 volts. So that is the E naught cell. Now we have to calculate delta G naught. Delta G naught formula is minus NF E naught. What is the N? The number of electrons transferred. So 2Cr value is changing to 2Cr3 plus. So there is a change of plus 6 oxidation state. From 0 it is changing to plus 6. That means there is a transfer of 6 electrons. Okay, it loses 6 electrons. Then these 6 electrons are gained by cadmium, changes to cadmium ion, that changes to cadmium. Okay, so minus 6 into 96500 into 0.34. So this comes out to be minus 196,860 joules or 196.86 kilojoules. Okay. Then how do you calculate the equilibrium constant? Delta G naught equals to minus 2.303 RT log Kc. So the Kc will be equal to minus delta G upon 2.303 RT. The negative sign cancels and you get 34.501. Now this is Kc, log Kc. Now you have to find out Kc by finding out the antilog of this value 34.501. So we'll see in the table 0.501, antilog is 0.17 and 3.17 and 34 goes as a power of 10, so 10 to the power of 34. Okay, fine. Okay, similarly we can calculate for the next reaction. Fe2 plus 2Ag plus gives you Fe3 plus Ag. Okay, the E naught cell is given, E naught of the half cells is given, so you can calculate E naught cell, E naught cathode minus E naught anode, which is cathode here and which is anode. The ones where oxidation is happening is always anode, so Fe2 plus changes to Fe3 plus, this is anode, and Ag plus changes to Ag is cathode. So Ag 0.80 minus 0.77, so this comes out to be 0.03 volts. Okay, then you can calculate delta G. Delta G is equal to minus NFE naught. N is how much? Number of electrons transferred is 1 into 96500 into 0.03. That comes out to be minus 2895 joules, or it can be minus 2.895 kilojoules. Okay, now put the value here. Okay, so this is log Kc equals to minus of delta G upon 2.303 RT minus 2895 upon 2.303 into R is 8.314 into T is temperature is 298 kelvins. Okay, so this comes out to be 0.5074. When you do the antilog of 0.5074, it comes out to be 3.22. So Kc is 3.22, right? So in this magnesium, write Nernst equation and EMF of the following cell at 298 Kelvin. Magnesium solid, magnesium ions 0.001 m for vertical line, then copper ions 0.0001 m, copper solid. So that means here the anode is magnesium and cathode is copper. So you have to write the Nernst equation. First write the cell reaction, then you will write the Nernst equation. So magnesium plus copper ions gives you magnesium ions plus copper. The flow of 2 electrons, so N is equal to 2. Formula is E cell equals to E naught cell minus 0.059 by N log to the base 10 magnesium ion concentration upon copper ions concentration. Okay. So E cell equals to E naught cell is what? E naught cathode minus E naught anode. Cathode concentration is potential is 0.34, anode potential is minus 2.37. So 0.34 minus 2.37 minus 0.0591 upon 2 log to the base 10 to the power of minus 3 upon 10 to the power of minus 4. The concentration of magnesium is 10 to the power of minus 3 and that of copper is 10 to the power of minus 4. Okay, so this comes out to be 2.71 minus 0.029955, and on adding these two you get 2.68 volts, right? Then the next one is Fe2 plus H plus H2. So that means iron is getting oxidized. The cell reaction is Fe gives you Fe2 plus 2H plus gives you hydrogen. So again there is a transfer of 2 electrons. So E cell equals to E naught cell minus 0.0591 upon 2 log to the base 10 Fe2 plus upon H plus square. So here the E naught cell will be what? E naught cathode minus E naught anode. So it is 0 minus 0.44 minus 0.0591 upon 2 log Fe2 plus ion concentration is what? 10 to the power of minus 3 and H plus concentration is 1 m. Okay. So this comes out to be 0 minus 0.44 minus 0.0591 upon 2 log 10 to the power of minus 3. So 0.44 minus 0.0591 upon 2 into minus 3. So that is 0.44 plus 0.0887. This gives you 0.5287 volts. Then tin plus 0.05 m, H plus 0.02 m, H2 1 bar. platinum. Okay. So here E cell, as what is the cell reaction? Tin plus 2H plus gives you tin 2 plus plus H2. So E cell is equal to E naught cell minus 0.059. There's a transfer of 2 electrons upon 2 log tin 2 plus upon H plus square. So E naught cell minus 0.0591 upon 2 log 0.05 is the concentration of tin ions and 0.02 is the concentration of hydrogen ions. Okay. So point 0 minus minus 0.14 minus 0.0591 upon 2 log 125. Then 0.14 minus 0.0591 upon 2 into 2.0969 when you take the log of this. So this comes out to be on solving 0.078 volts. Clear? Then platinum, bromine, bromide 0.01 0 m, H plus 0.030 m, hydrogen gas 1 bar platinum. So my equation is what? 2Br minus plus 2H plus gives you Br2 plus H2 and N is equal to 2. So write the next equation. E cell equals to E naught cell minus 0.059 upon 2 log Br minus square 1. This is bromine, hydrogen. This is the standard state. So this is concentration is unity for the then Br minus square upon H plus square. 0 minus 1.08. This is a E naught cell. Cathode minus anode. Cathode is hydrogen electrode, so 0. Bromine electrode 1.08. Okay. Minus 0.059 upon 2 log 1 upon 0.01 square into 0.03 square. So this comes out to be 1.08 minus 1.08 minus 0.0591 upon 2 log 1.111 to 10 to the power of 7 minus 1.08 minus 0.059 upon 2. Now when you take the log, it is this 10 to the power of 7 is 7.0457. So this comes out to be 0.208. So this on adding this to minus 1.22288 volts. So thus oxidation will occur at hydrogen electrode and reduction will occur on bromine electrode. So this setup is not correct because EMF is coming negative. EMF should be positive. That it is coming negative, that means this setup is not correct. Hydrogen should have been anode and bromine should have been cathode. Okay. Now, in the button cells widely used in watches and the other devices, the following reaction takes place. Zinc solid, Ag2O plus water gives you zinc ions plus 2Ag plus 2OH. So you have to determine delta G naught and E naught. So my cell reaction is what? Zinc is converting to zinc ion plus 2 electron. The EMF is oxidation potential is 0.76 volts. Then Ag2O plus water plus 2 electron gives you Ag plus 2OH minus. So E naught is 0.344 volts. So here is given the oxidation potential while here it is given reduction potential. So we should first convert this oxidation potential to reduction potential by inversing the sign 0.76. Okay. Or we can say the another formula E cell equals to E naught reduction minus E naught oxidation. E naught cathode minus E naught anode. So this is 0.344 minus 0.76 gives you 1.104. Okay. Once E naught cell is calculated, we can calculate G naught by the formula delta G naught equals to minus NF E naught. So N is 2 because the electrons transferred are 2. So 2 into 96500 into 1.104. That means 2.13 into 10 to the power of 5 joules. Clear? So using the standard potential, electrode potential given in the table, predict if the reaction between the following is feasible or not feasible. Okay. So Fe3 plus and I minus. So when you do the reaction between I minus and Fe3 plus, you get Fe2 plus and half I2. So Fe3 plus is changing to Fe2 plus, Fe3 plus is reducing and I minus is oxidizing. So I minus is anode and Fe3 plus is cathode. So E cell is equal to what? E cathode minus E anode. 0.77 minus 0.54, that is 0.23 volts. That means this is positive E naught cell, that means it is feasible. Now copper solid, copper and silver. Copper solid plus 2 Ag plus gives you copper plus 2 Ag. Okay. So my cathode here is 2 Ag plus and anode is copper. So cathode potential minus anode potential is 0.80 minus 0.34. That comes out to be 0.46 volts. So this cell is also feasible. Okay. So when you use copper as anode and silver as cathode, then the cell is feasible. Then bromide plus Fe3 plus gives you Fe2 plus plus half bromine. So here bromine is getting what? Bromine is getting what? Oxidized Fe3 plus is getting reduced. So 0.77 minus 1.08 cathode minus anode. Okay. So that means minus 0.314 volts. So this is not positive. That means it is not feasible. Then Ag and Fe3 plus. 3Ag plus Fe3 plus gives you 3Ag plus plus Fe. So this will be again Fe3 plus is getting reduced and Ag is getting oxidized. So 0.77 minus 0.80. Okay. So minus 0.03. Again this is not feasible. Then Fe2 plus and Br2. Fe2 plus is changing to Fe3 plus, Br2 is changing to Br minus. Okay. So this is 1.08 minus 0.77. Okay. So this is 0.31 volts. Again this is feasible. So likewise children, by calculating the EMF of the cell, you can find out whether it is feasible or not feasible. Yeah. Okay. Now we will study the electrical resistance. What is electrical resistance? So this is the conductor. This is having length L and area of cross section A. So resistance is directly proportional to the length of the conductor and inversely proportional to the area. So R is directly proportional to L upon. So electrical conductance. Now what is conductance? Conductance is represented by G and it is the ease of flow of current. Okay. So according to Ohm's law, R is equal to V upon I. This we already know. The unit of V is voltage is volt and current is I is the current and the unit is ampere. So volt per ampere is and R is R resistance and its the unit is another unit is ohm. So electrical resistance is ohm denoted by the symbol omega. Thus omega is equal to volt per ampere. So electrical conductance of a solution is reciprocal of the resistance. G is equal to 1 upon R. And the SI unit of G is what? Ohm inverse. We can also call it as Mho, MHO, or the other unit is Siemens. Okay. Conductance of electrode depends on the nature of electrolyte added, nature of solvent and its viscosity, concentration of electrolyte, size of ion produced in its solution. So these and temperature. So all these affect conductance. Conductance is ease of flow of current. So conductance is usually measured in ohm inverse or Siemens. So just now we said R is directly proportional to L upon A. So that means R is equal to rho L upon A. What is rho? Rho is the resistivity or specific resistance of the conductor. So rho is equal to what? R into A by L. So if L is equal to 1 meter and area of cross section of the conductor is 1 meter square, then rho is equal to R. Conductivity. Electrical conductance of the sample G decreases as its length increases with its cross-sectional area. That means G is directly proportional to A and inversely proportional to L. Or we can also say G is equal to K into A into L. Okay. So what is K? K is G into L into A. G is conductance and L upon A is cell constant. G can also be written as 1 by R L upon A because G is equal to 1 upon R. Okay. So proportionality constant K is also called conductivity of the conductor. If L is equal to 1 and A is equal to 1 meter square, K is equal to G. So conductivity is defined as the conductance of a unit cube of material. Okay. So let us compare or relate conductivity and resistivity. So resistivity is what? R is equal to rho L upon A. Okay. K is equal to 1 by R L upon A. That means rho is equal to R A into L, while K is equal to 1 upon R L upon A. So K is inversely proportional to resistivity. Thus conductivity is inverse of resistivity. So the unit for resistivity, conductivity will be what? Siemens meter inverse or ohm inverse meter inverse. Or we can say ohm inverse centimeter inverse. Normally the cells that we take are very small in size. So we say centimeter inverse. Ohm inverse, centimeter inverse. So conductivity of the electrolytic solution is what? 1 upon R into L upon A. Conductance into cell constant. For a given cell, L upon A is a cell constant. The value of length of the electrode. L is what here? Length of the electrode. And A is a cross-sectional area between them. So L upon A. This value is constant for a particular cell. So you call it as cell constant. And the unit is what? Meter inverse or centimeter inverse. So conductivity of the cell can be given by, instead of writing 1 upon R, L upon A, we can say cell constant upon R. Okay. Molar conductivity. Now what is molar conductivity? High concentrated solution, if we are having, that will have more ions and the conductivity is going to be higher. Low concentrated solution, if we are having, they will have less ions and the conductivity is going to be less. So Kohlrausch introduced new term molar conductivity, which is denoted by lambda. So molar conductivity is the conductivity of the solution containing 1 mole electrolyte. So in the electrolytic conductivity divided by the molar concentration of the dissolved solute is called molar conductivity. So molar conductivity is conductivity produced by a solution containing 1 mole of electrolyte. So it is represented by lambda. So lambda is equal to K upon C, or we can also say kappa upon C. Unit for kappa is what? Siemens meter inverse. Unit for concentration is what? Mole per meter cube. So the unit for lambda will be what? S meter square per mole. So molar conductivity unit will be what? Siemens meter square per mole. And the CGS unit will be ohm inverse centimeter square per mole. Clear? Now what is the difference between conductivity and molar conductivity? So conductivity is a measure of electrolyte's ability to conduct electricity through it. And molar conductivity is the ability of electrolytic solution measured per unit concentration. Molar concentration. So ability of an electrolytic solution that is measured per unit molar concentration. The unit of conductivity is what? Siemens per meter or ohm inverse meter inverse. While the unit of molar conductivity is what? Siemens meter square per mole or ohm inverse centimeter square per mole. Molar concentration. Molar concentration of solution is not considered while checking conductivity, while molar concentration of solution is considered when you are taking molar conductivity. What are the uses of conductivity? It is mainly used to determine the presence of conductive ions in solution. And here it is used to help to determine the dissociation constant. Variation of conductivity and molar conductivity with concentration. Now, conductivity always decreases with decrease in concentration, both for weak electrolytes and strong electrolytes. Actually, conductivity is a conductance of 1 meter cube of a solution. Okay, 1 centimeter cube of a solution. So when the conductivity, so basically we are seeing the number of ions in unit volume. So when you decrease concentration, the number of ions unit volume decreases. Therefore, conductivity decreases. So whether it is a weak electrolyte or a strong electrolyte, when you add water, basically the concentration of ions decreases, the number of ions per unit volume decreases, and hence the conductivity decreases. This is due to the fact that number of ions per unit volume that carry the current in a solution decreases on dilution. Now, molar conductivity of a solution at a given concentration is the conductance of volume V of solution containing 1 mole of electrolyte. How does it vary with decrease in concentration? Decrease in concentration means increase in volume or increase in dilution. So, molar conductivity increases with decrease in concentration. This is because the total volume of the solution containing 1 mole electrolyte also increases. So, it has been found that decrease in K conductivity on dilution of a solution is more than increase in its volume. Okay. Now let's see the two graphs. So strong electrolyte you see when you're decreasing concentration, molar conductivity is increasing. Okay. And it will reach a limiting value. That will be the molar conductivity at infinite dilution. So when you extrapolate this graph, you can calculate the molar conductivity at infinite dilution for strong electrolyte. So why is it that for strong electrolyte the molar conductivity increases when you are increasing dilution? Because strong electrolytes, the ions, it is already completely dissociated. So it is not like on dilution the number of ions increase. Number of ions are already there. But when you are adding water to it, the distance between the ions increases. So the flow of current becomes easier. So when you dilute strong electrolytes, the conductivity increases. Okay. And how will you find out the molar conductivity at infinite dilution? By extrapolating this graph to 0. So that will be molar conductivity at infinite dilution or 0 concentration. Then for weak electrolyte, what happens when you are increasing water or increasing the solvent? What happens? The dissociation increases as per as the Oswald's dilution law. So dissociation increases on increasing the on decreasing the concentration or increasing the volume. Okay. So when you are increasing the volume of water, the molar conductivity increases. But you are not able to find out the molar conductivity at infinite dilution with the help of this graph. Okay, because after this increase certain point, this graph becomes parallel. And therefore it cannot be calculated. The infinite molar conductivity at infinite dilution cannot be calculated for weak electrolytes from this graph. Okay. So molar conductivity reaches a limiting value at 0.001 and 0.0001 m. Okay. Then limiting value means, what does the limiting value means? It means that the further dilution will have no effect on molar conductivity. Even if you dilute it after that, there will be no effect. So the maximum limiting value of molar conductivity at 0 concentration or infinite dilution. It is denoted by lambda 0, and lambda is equal to lambda naught plus a square root c. So from this, this is Owen-Sager's equation. This means the molar conductivity at a particular concentration. The lambda naught is the molar conductivity at infinite dilution, and square root c means it is a concentration. C is concentration and A is the constant. Okay. So when you see the graph of the weak graph of the strong electrolytes, it comes to be lambda at any particular C. Lambda 0 is calculated from the graph, and square root C, and putting the value of A, you can get the molar conductivity at a particular concentration. Okay. So Y is equal to mx plus C. Okay. So this C is the intercept which gives you the value of molar conductivity at infinite dilution for weak electrolytes. So where A is constant, C is molar concentration, lambda 0 is the molar conductivity at 0 concentration. Okay. So when concentration of solution approaches 0, molar conductivity is called limiting molar conductivity, and it is represented by lambda m naught. Okay. Now for a strong electrolyte, lambda naught m naught can be calculated, determined by extrapolating the graph as lambda m varies linearly. But for weak electrolyte, the graph obtained is a curve, so it cannot be extrapolated to zero concentration. So for weak electrolytes, Kohlrausch law of independent migration is used to determine the molar conductivity at infinite dilution. So Kohlrausch law of independent migration of ions. So Kohlrausch says actually that each ion contributes towards the conductivity. So the law states that limiting molar conductivity of an electrolyte can be represented as a sum of individual contribution of anions and cations of the electrolyte. So let's say if it is NaCl. NaCl is made up of Na ammonium chloride. Let's say it's ammonium chloride. And ammonium chloride is made up of ammonium ion and chloride ion. So the molar conductivity of ammonium chloride will be equal to the ionic conductivity of ammonium ion plus ionic conductivity of chloride ion at infinite dilution. Okay, so this law was given by Kohlrausch. At infinite dilution, each ion migrate independently of its co-ion and make its own contribution to the total molar conductivity of an electrolyte, irrespective of the nature of the ion with which it is associated. So every ion contributes. So lambda naught m molar conductivity at infinite dilution is equal to the ionic conductivity of the sum of the ionic conductivities of the various ions which it is made up of. So where lambda plus and lambda negative are the molar conductivity of cation and anion respectively at infinite dilution. So in general, for an electrolyte BXAY giving X number of cations and Y number of anions, the infinite molar conductivity at infinite dilution is equal to X lambda naught plus Y lambda negative naught. So lambda naught Na plus lambda naught Cl minus are limiting molar conductivity of sodium and chloride ion respectively. So then the limiting molar conductivity of sodium chloride is given by the equation lambda naught m NaCl equals to lambda naught Na plus lambda naught chloride minus. So in general, if an electrolyte on dissociation gives nu plus cations and nu negative anions, then its limiting molar conductivity is given by molar conductivity at infinite dilution is equal to nu plus lambda naught plus nu minus lambda naught minus. So lambda plus naught plus and lambda minus lambda naught negative are the limiting molar conductivities of cations and anions respectively. Application of Kohlrausch's law. Now how Kohlrausch's law is helpful. It is lambda m naught for weak electrolyte is obtained by using Kohlrausch's law of independent migration of ions. Okay, so it is helpful in calculation of molar conductivity of the solution at infinite dilution for weak electrolytes. Then it can help you to calculate the degree of dissociation by using the formula alpha is equal to lambda upon lambda naught m. Alpha is the degree of dissociation, lambda is the molar conductivity at that concentration, and upon lambda m the molar conductivity at infinite dilution. It helps you to calculate the dissociation constant for weak electrolyte. We all know dissociation constant is equal to what? K is equal to alpha square C upon 1 minus alpha. So this is K is equal to, putting the value of alpha here, K is equal to lambda square C upon lambda infinite dilution is in bracket lambda infinite dilution minus lambda at a particular concentration. So you can calculate K, that is the dissociation constant. Then it helps you to calculate the ionic product of water, solubility product of the sparingly soluble salt. So these are the applications of Kohlrausch's law. Now this numerical. Here molar conductivity for NaCl, HCl and sodium acetate are given 126.4, 425.9 and 91 Siemens centimeter square per mole. They've asked you to calculate the molar conductivity at infinite dilution for acetic acid. Now for acetic acid, it is equal to ionic conductivity of H plus and ionic conductivity of acetate ions. The summation of these two will give you the molar conductivity of acetic acid at infinite dilution. Now here what all is given to us? Na plus Cl minus, their summation is given. Then H plus and Cl minus, their summation is given. And Na plus and Ac minus Cl summation is given. And we have to find out HAC. So how will you find out HAC? If you, so this all is given. So if you add, you have to get H and AC. H and AC. Okay. So if you add HCl and NaAC and subtract NaCl, you will get HAC. Okay, see here. So if you add HCl and NaAC, their molar conductivities, and subtract NaCl, you will get HAC. Yes. So 425.9 plus 91 minus 126.4 will give you the molar conductivity at infinite dilution for acetic acid. Okay. Very important numerical. Now, how to determine conductivity of a solution? Let us try to understand the basics by knowing what is conductivity cell, what is cell constant we already know, then what are the steps to calculate the conductivity of given solution. Now, measurement of conductivity of ionic solution, there are two main problems. One is that you cannot pass DC current. Passing of DC changes the composition of the solution. Then solution is difficult to connect to a bridge. So you should pass AC current instead of DC current and you use conductivity cell instead. So three main steps are: first we will determine the cell constant, then we will determine the conductivity of the solution, then we will determine the molar conductivity. So how will you do it? Let's see. Now we have to use the Wheatstone bridge here. So according to Wheatstone bridge principle, so Wheatstone bridge, you see here the resistance are given, and the unknown resistance is of the conductivity cell. Okay, so R solution upon RAC. Okay, so when you are connecting here to null point, this is AC, this is BC, this is RX, and this is R solution. So R solution upon RAC is equal to RX upon RBC. So resistance of conductor is proportional to its length. So RAC is equal to length AC and RBC is equal to length BC. Okay, so using the null point, we can find out the point where we get the null point, and that's how we can put the values of resistance and calculate the resistance of a solution. Okay, so R solution upon length of AC, Rx is the resistance that we are introducing, and length of BC. So R solution is calculated. Then, so by measuring the length of AC, BC and knowing Rx, the resistance of KCl can be calculated. What we have taken here in the conductivity cell, the electrolyte we have taken is KCl. Cell constant will be constant for this cell. Cell is constant is what? Length of the electrode upon cross-sectional area. That is a constant for a particular cell. So this will be given. So B is equal to KR. B is the cell constant here. K is the conductivity of KCl and R is the resistance of the solution. So if you know the resistance of the solution and if you know the cell constant, you can calculate K. So okay. So this is the conductivity cell. Here you see the glass tubes, solution and the electrode, platinum electrode. So conductivity cell contains basically the glass tube with two platinum plated coated with thin layer of finely divided nickel. So how do you put platinum black? This is achieved by electrolysis of solution of chloroplatinic acid. The cell is dipped in the solution whose resistance has to be measured. So this is a conductivity cell. Now determination of the conductivity of the given solution. Determination of the cell constant, the various steps are there. Reference solution KCl is then replaced by solution whose conductivity is to be determined. By using the Wheatstone brush principle, the resistance of the solution is determined. Conductivity of the solution can be calculated by using the formula. K is equal to B upon R. B is what? Cell constant. R, solution you have found out. So B upon R will give you the conductivity. B is cell constant. Cell constant is denoted by B, that is L upon A, length of the electrode upon area of the electrode. Also it is represented by G star. Since concentration of the solution is already known to you, molar conductivity can be calculated using the formula. Molar conductivity is equal to K upon C. So just now we calculated K from the previous formula, and then we will calculate the molar conductivity, dividing K with the concentration of the solution. Now let us solve some numerical. A conductivity cell has two electrodes 20 mm apart and cross-sectional area is 1.8 cm square. So find the cell constant. What is the formula for cell constant? Cell constant is equal to this length upon area. Okay. So distance between two electrodes is how much? 20 mm, that is 2 cm. And cross-sectional area is how much? 1.8 cm square. So you can calculate B, L upon A. So 2 upon 1.8, that is 1.11 centimeter inverse. Okay, let's go to the next numerical. A conductivity cell is filled with 0.1 m KCl. It gives 25 degrees centigrade at 25 resistance of 85.5 ohms and conductivity of 0.01286 ohms inverse. The same cell filled with 0.00 m 5m SCl gives a resistance of 529 ohms. What is the molar conductivity of SCl solution? So R KCl is given, K KCl is given. Okay, concentration of SCl is 0.005 m. Resistance of SCl is 529 ohms. You have to find out the molar conductivity. Okay. So conductivity of the cell is equal to cell constant upon resistance. So B upon R. B is equal to K into R. So K is given here. Multiply with R will give you the B, that is the cell constant, 1.1 centimeter inverse. Clear? Now, what else we have to calculate? We have to calculate K of SCl solution. So you found out the cell constant, cell is going to be the same, only the solution is changing. So for K SCl will be B upon R SCl. So B is already calculated 1.1 and K SCl is given 529. R SCl is given 529 ohms. So 1.1 upon 529 gives you 2.08 into 10 to the power of minus 3 ohm inverse centimeter inverse. Okay. So molar conductivity is what? K into 1000 by C. So K is calculated into 1000 upon C, 0.005 m. So that is 416 ohm inverse centimeter square per mole. Clear? So these are some of the questions which you can solve. The homework. Now let us revise all the formulas. Resistance is equal to V upon I. R is unit of R is ohm, V is volt and I is ampere. So the other unit for R is volts per ampere. Electrical conductance is represented by G and it is equal to inverse of R. So G is conductance. Conductance is the ease of flow of current. R is the hurdle in flow of current. So G is inversely proportional to R. Then conductivity is equal to what? G into L by A, or also we can write 1 upon R, L upon A. Then resistivity is what? R A to upon L. Okay. So that means K is inversely proportional to resistivity. So conductivity is inverse of resistivity. Then molar conductivity, the formula is K upon C or K into 1000 upon C. Then on-Sega equation, molar conductivity of a particular concentration is equal to molar conductivity at infinite dilution plus A square root C. So lambda 0 is molar conductivity at 0 concentration or infinite dilution. Then lambda 0 is equal to x lambda plus y lambda minus. So lambda plus naught and lambda minus naught are the molar conductivities of cations and anions at 0 concentration. Okay. Cell constant is represented by B, or it is also represented by G star. So that is equal to K into R, kappa into R. Okay, let us solve some more numericals. The conductivity of 0.2 m KCl at 298 Kelvin is 0.0248 Siemens per centimeter. Calculate its molar conductivity. So what is given here? Concentration of the solution is given and K is given. Okay, so you have to find out molar conductivity. Very simple. The formula is molar conductivity is equal to K into 1000 upon C. So 0.0248 into 1000 upon C 0.2. So that comes out to be 124. Unit for molar conductivity is Siemens centimeter square per mole. Clear? Then the resistance of conductivity cell containing 0.001 m KCl at 298 Kelvin is 1500 ohm. What is the cell constant if conductivity is 0.001 m KCl at 298 is 0.146 into 10 to the power of minus 3. So cell constant is what? Conductivity upon conductance or conductivity into resistance. So conductivity is given 0.146. Resistance is given 1500. So cell constant will be 0.219 centimeter inverse. Clear? Okay. Then here conductivity of NaCl at 298 Kelvin is given at different concentration. So you have to calculate the lambda m for all concentration, draw plot, and then you calculate the lambda m naught, that is molar conductivity at infinite dilution. So for various concentration, it is given, K is given, and you have to calculate the molar conductivity. Then you have to plot the graph between molar conductivity and the concentration, square root of concentration, and then you have to calculate the infinite concentration. So at various points you have calculated here the molar conductivity at various concentration, then extrapolating it to 0, you get the molar conductivity at or infinite dilution. Okay. Calculate conductivity of 0.00241 m acetic acid is 7.896 into 10 to the power of minus 5 Siemens centimeter inverse. Calculate molar conductivity if the molar conductivity for acetic acid is given as 390.5 Siemens centimeter square per mole. What is its dissociation constant? So molar conductivity at different concentration can be calculated by kappa into 1000 by molarity. Kappa is 7.896 into 10 to the power minus 5 into 1000 upon 0.00241. This comes out to be 32.76 Siemens centimeter square per mole. Then you can calculate alpha, lambda mc upon lambda m naught. 32.76 upon 390.5, that is 8.4 into 10 to the power of minus 2. Then Ka is equal to C alpha square upon alpha. 1 minus alpha. Alpha is how much? Alpha you've calculated as 8.4 into 10 to the power of minus 2. That is 0.084. So 0.0024 into alpha square. Put the value upon 1 minus alpha. Gives you 1.86 into 10 to the power of minus 5. Okay.